Here's an interesting kinematics problem that was given to students sitting the physics Olympiad many years ago. And since then, it became a classic in a way. And there have been many ways in which this problem has been rephrased. And if you'd like to see anything similar to this, or if you have any ideas for other topics or specific problems that you'd like to see on the channel, please let me know in the comments. So we're dealing with a dog who is running with a constant speed v, and the dog is chasing a cat that is running with a constant velocity u. Now, we're also given that the dog always heads towards the cat, and we're asked to find the acceleration of the dog when the two velocity vectors are perpendicular to each other, knowing that at this moment the distance between the dog and the cat is lowercase r. So this is how the situation could look like, right? Now the question tells us that the velocity of the cat is constant. In other words, not only is the speed constant, but the direction doesn't change either. In other words, the cat is always running in a straight line. And without losing any generality, I decided to make that trajectory of the cat as a straight horizontal line, right? And at this particular moment, I said the cat is at point B. Now, the dog has a constant speed, but not a constant velocity, because the dog is always headed towards the cat. So, for instance, when the cat will be here with the same velocity u, try to make this nice and horizontal. At this moment, the dog might be somewhere here like this. So the speed of the dog is the same, but the velocity, that's why I put a prime, it's a different velocity because it has a different direction, so it's a different vector. And we are asked to find the acceleration of the dog in this moment here. So let me just erase this part. And some students get confused because how can the dog have an acceleration if the speed doesn't change? But although the speed is the same, the velocity of the dog does change. So the acceleration can actually be split in two components. So we've got our tangential acceleration, which is given by the change in speed. So the tangential acceleration, that is the acceleration along this direction, is given as dv by dt, and that is actually equal to 0 because the dog does not speed up or slow down. So there's no component of the acceleration along the direction of the velocity of the dog, which means that the only acceleration component of the dog can be perpendicular to the velocity, and that's the normal acceleration, right? And we actually know what the formula for the normal acceleration is. It is v squared over r, where r is the radius of curvature of the trajectory. So this is the radius of curvature. Note this is not the same as lowercase r because that's just the distance between the dog and the cat. And this is also omega squared r or omega v. And it will turn out that this is actually the formula that will be easiest to use in our case. So we know v, right? So we know half of what we need to find the acceleration of the dog. So we decided to use this formula, and this is what we know. So it's the angular velocity of the dog in this moment that we have to find out. And to do that, surprisingly, we can use Euler's equation of motion for velocity, okay? And here's how that will look like. I will, first of all, place my coordinate system on point A, right? And that coordinate system is going to look like this. So I have my point A here, this is where the dog is, and then I've got my Y and I have my X. Those are my positive X and Y directions, and then the cat is somewhere here, and we know the distance to the cat as being lowercase r. So here's what we can write. We can write that the velocity of the cat, the velocity of B, is equal to the velocity of A plus the relative velocity of b with respect to a, and I'll comment about this in a second, plus omega cross AB. So that second term on the right-hand side, that actually refers to how the distance between the cat and the dog changes with respect to time. So it only refers to the distance either getting longer or shorter, right? In other words, this velocity only has a component in the y direction, given how we defined our coordinate system. So I'm going to call this vector vrel and then multiplied by j, because this is how this component in Euler's equation for relative velocity is defined, as you can find in any source. So we don't really care too much what this is, although it's easy to find, but we'll just treat it as something, some scalar multiplied by the j unit vector. So let's look at everything else and let's see how everything fits together. So VB, that's the velocity of the cat, obviously, which is pointing in this direction. And the velocity of the cat is given to us as u, which means that in this case, VB is actually u times I, because the velocity of the cat is purely in the x direction, and that's equal to the velocity of the dog, which is v times j, plus this relative velocity times j, plus, and then we're going to have our determinant here, which is ijk. I don't know anything about omega, so I'm just going to consider omega to be positive by default. And then ab is the vectorial distance from a to b, which is just r in the y direction. So that 0, r, and 0 again. So we can solve this quite easily. We have u times I equals v times j, and then we have our relative velocity times j again. And then the determinant will just have this I component that is going to be I times, and if we do the multiplication, that will give us minus omega r. Okay, now we can equate the I terms. So we've got that this u has to be equal to this, which means that u is minus omega r, which means that omega is minus u over r. And this minus actually tells us that the angular velocity of the dog in this moment is clockwise, right? Which makes sense in a way, because if you can imagine, as the cat runs to the right, the velocity vector of the dog will start rotating clockwise, which is why we have a minus here. So if we only care about the value, we can say that, okay, the absolute value of omega is just u over r. So the normal acceleration, therefore, which is omega v, is going to be u v over r. And that's the acceleration of the dog in this particular moment. So it only depends on the distance between the two, as well as on the speed of the dog and the speed of the cat. And that's it. Now, we can take this one step further by looking at a generalization of this problem. So in this case, we're dealing with the same scenario as before. So there is a cat that's running with constant velocity u, and we have the dog that's running with a constant speed v. But rather than looking at what happens when the two directions are perpendicular to each other, let's look at what happens with the acceleration of the dog when the direction of the cat and the direction of the dog make a random angle theta. So let's say that in this case, you've got the velocity v being pointed like this, and you've got this angle here being theta, okay, which is the same, by the way, as this angle. So we're going to deal with this exactly the same way, and then you will see how we can obtain this result from the more general result that we get from this problem. So I'm going to call this point A, this point B, and then I will apply Euler's equations like before. And before I do that, I have to define my coordinate system. And I think the easiest way to do it is to just place a coordinate system at A. So imagine this is at A, right? But more importantly, the directions of my X and Y axis. So X is along this direction, right? So let's say this distance from here to here is given to us as lowercase r again. And Y is perpendicular to that direction, okay? Same as before, there is no tangential acceleration for the dot. So the tangential acceleration is 0 because the speed is constant. However, there is a normal acceleration, which is omega times v. We know v, therefore we're trying to find omega. So let's apply the Euler's equations, which are as follows, or just one equation for velocity. So we have the velocity of b is equal to the velocity of a plus the relative velocity, and then plus omega cross AB. So remember, we're trying to solve everything along the x and y coordinate system that we have here. But to do that, we have to note that the velocity of the cat is actually horizontal, right? Which means we have to find the components in the x and y directions. And here's how we can do that, and it's very easy. So along the x-axis, the velocity component of the cat is going to be like this, which is, get rid of this here, so this will be just u cos theta, and then this component here is going to be u sine theta. Now, when we use this u sine theta, we have to remember to put a minus sign because it's going this way, which is against my positive y direction. Okay, so let's see what we have. The velocity of b will be as follows. So u cos theta times I, right? This is the velocity of the cat, and it has an x component, which is u cos theta, and then minus, I have u sine theta times j, okay? And that will be equal to the velocity of the dog, which is v times I, plus. Now, the relative velocity is the same as before. This component of relative velocity only takes into account the change, the lengthening or the shortening of the distance between the dog and the cat. So it only has an x component in this case. So this is v rel times I plus, and I'll just write omega cross AB here, and then we'll do it on the next page. So let me just take this with me, and let's see how we can expand this a bit more. Now, this omega cross AB, this is, of course, the determinant ijk, and then omega is what we're trying to find out, and AB is the distance between the dog and the cat, right? And it's in the x direction, so it just has a value of r, and then everything else is 0, okay? Which means that this determinant only has a j component, which is j times omega r. So if we put everything together, this is what we get. We get u cos theta I, and then minus u sine theta j, and this is equal to vi plus the relative velocity times I, plus, and then we have omega r times j. And the easiest way to do this is to just look at the vector components. So we've got a j component here, and we've got a j component here. So the two have to be equal to each other because there's equality between the two expressions. So we've got minus u sine theta is equal to omega r. So omega is therefore going to be minus u sine theta over r. So that's the angular velocity of the dog when the angle between their two directions is some theta value. So now that we know this, first we're going to ignore the minus, so we'll just look at the value of omega, and therefore we have that an, which is omega v, will be equal to u sine theta over r times v, which is uv sine theta over r. So this is the acceleration of the dog for any angle. Okay, so the condition is that the dog must always head towards the cat. And as you can see, if you try to look at this problem again, right? So in this case, the angle between the direction of the dog and the direction of the cat was 90 degrees, which means that if we put 90 degrees in here, we should get the same answer as in that first particular case. So if theta is 90 degrees, then sine of theta is 1, which means that an is uv over r, which gives us the answer for the first question. And this is the answer for the general problem. That's it.